We've seen now in earlier videos how integrals might be things that we want to compute. Over this next series of videos, we're going to explore how we can compute them under different scenarios, what kind of rules apply for manipulating the formal descriptions of these integrals. Let's start off with a fairly easy idea relating back areas to integral values. Remembering that the integrand here, the function inside the integral, is what we would draw if we're asked to sketch something related to an integral by default. So the cos graph is the graph that starts high and then goes down. In this case, pi over 2 and negative pi over 2 are when it goes to 0. Then we can look at the bounds of the integral, or the interval. Here would be negative pi over 3 to pi over 3. So around here. And what we're being asked to compute with this integral is the area between the axis and this graph, between negative pi over 3 and pi over 3. So let's add an extra ingredient. What if you were told that the integral from 0 to pi over 3 of cos of x dx were equal to a particular value, here root 3 over 2. Can you relate that to the area that's on the graph here? Pause the video and we'll check in a moment. Okay, so what we've been told with this piece of information is that if we look at the graph of cos of x from 0 to pi over 3, so 0 this time is the starting point, this area is equal to the square root of 3 over 2. Well, what we see is there's also an equal area on the opposite side, which would be another root 3 over 2. In other words, we'd see that there's this area and this area is perfectly matched because of the symmetry of the cos function. And so what we would end up with is 2 times the amount we found on the right-hand side here. That idea of looking at the whole interval and breaking it into subintervals leads us to a more general property when we're looking at evaluating integrals. When we have an interval from a to b, it's possible, if we find it helpful, to split that. It doesn't have to be split in the middle necessarily. It can just be at some other point c. And if you look at what we're writing out here in formal notation, the integral from a to b, if we add up all the contributions from a to b of the area underneath the graph, then we can get that a different way if it's more helpful. We can go from a to c and get that first of our function integral here, and then we can add in what would happen if we went from c and the remaining distance, or the remaining interval, pardon me, c to b of our function here. So if it's helpful, we can take a long interval and subdivide it anywhere we like, find the integral from the start to that interior point, and then add on the integral from that interior point to the end of the interval, and we'll end up with the same quantity. There's an interesting variation on this theme, which is the order of the limits of integration. So a less commonly used but equally true corollary is the idea or the ability to have an integral that goes from one point to a second point. If we want to reverse those for whatever reason, and there are some reasons sometimes, then we can do that. We can exchange the a from the bottom, put it up top, take the b from the top, put it down the bottom bound, but then we will flip the sign. So reversing the bounds results in a flipping of the sign. Now, in some sense, this has to be true because of what we saw in the previous example. If we integrate from 0 to pi over 3 and then pi over 3 to 0, again, this is the one we have to think about what it means. We'll do that soon. But just from a purely logistic step, imagine going from a to c and then c to b, which is what we had in the last example. If we had the same endpoint here, sorry, let's finish this off, cos of x dx. If we have the same endpoint here and here, I'm just going to go back a page, same endpoint here and here, then we can collapse the integral and just make this equal to the integral from the first starting point, 0, to the last ending point, also 0. And, well, that's the area under the graph from the point 0 to the point 0. And that has 0 area. Essentially, by definition, if there's no width, it doesn't matter what the height is, we're going to have 0 area. And if that's the way the system is going to work, then what we should be able to do is capture that a little bit earlier in the calculation process and write this as the integral from 0 to pi over 3 cos of x dx, but with a minus sign out front. Then we would actually say that this area, pi over 3, sorry, that this area and this area are the same. In some sense, I'm counting this one in a positive direction, and this one I count in the negative direction because I flipped the order, and so we would end up with something minus the same thing. Those would cancel. We would end up with 0. Well, why does that make sense? Is there a reason based on how we build integrals that this is a reasonable choice? And absolutely. If we build up our sums over an interval, you can imagine how we built this before. When we subdivided this into small delta x intervals, we had delta x was equal to b minus a over the number of intervals. And if b was to the right and a was to the left, then b minus a was a positive quantity. But if I want to integrate from b back down to a, which is what we're exposed to now, if I want to integrate, so comparing and contrasting here, that was like the integral from 0 to pi over 3. If we go from pi over 3 to 0, that's going somehow backwards. And so our delta x here is a negative quantity. If we want to bring that negative out front, we can bring that negative out front and then turn it into the positive direction, 0 to pi over 3. So we can change the order, but if we do that, we're also changing the sign of the delta x or the dx in our integral. And so we have to account for that by popping a negative sign out front. So it does have some nice roots back in the Riemann sum formulations that we use to construct integrals in the first place. You can also just think of it as a mechanical transformation. If I swap these limits, I can do that, but I'm also going to pop out a negative sign, whichever makes more sense to you.